Hello, good afternoon everyone, and welcome to this webinar. My name is Adam Martin, and I'm a Technical Manager for Maya HTT. Today we'll be sharing some practical examples of how front-loading simulation works and the value of multi-physics simulation and how Maya could help you reevaluate your engineering processes for front-loading of simulation. There will be some interactive polls throughout this presentation to keep it interesting and some time for questions and answers at the end. If you have any questions as we go along, please do not hesitate to ask them via the Ask a Question tab on the overview window in the right-hand side of your screen. And hopefully we'll be able to get around to answering them at the end of the session for you. Before jumping into more detail, I'd just like to give you a quick introduction to Maya HTT and who we are. So Maya provides software-driven engineering solutions to our customers. Last year, we were proud to be awarded Worldwide Software Partner with Siemens, and we resell a lot of the Siemens SimCenter portfolio. We're a large team of passionate scientists and engineers based around the world. Maya started out in the space industry, but now is recognized for our multi-physics simulation capabilities, and we have many engineers with hands-on experience in various industries. We've developed over 30 software modules for the Siemens SimCenter portfolio mainly, and we've helped our customers put satellites into space, reduce energy consumption in their data centers, design zero-emission vehicles, and help them find better ways of engineering better products. Just a quick overview of some of the services and things that we offer our customers and work with our customers on daily. So, in the world of design, with the NX Siemens tools and Solid Edge, helping customers improve their design processes. Simulation, getting it right before you build, very much the focus of today's webinar. We've many years of experience in the manufacturing, CAD/CAM area, and offer consultancy and services in this. More recently, we've moved into industrial IoT, and we've been doing some very interesting projects in that space around predictive maintenance, and have some really strong track record of implementing actual IoT and applied AI projects. For many years in our DNA is software development and customization of applications, particularly around the Siemens portfolio. And we have very experienced agile teams which can deliver continuous software to our customers, as well as the automation and optimization of tools. We can help with our knowledge of the simulation tools to improve your simulation processes. And we've seen particular success in those areas, managing to reduce manual work, speed up processes. And finally, product lifecycle management, or PLM. So Maya has about over 150 PLM projects that we've been involved in, multi-site, multi-CAD implementations. So we're right there with you throughout the process of designing and bringing a product to manufacture into the market, and then learning from that and improving your designs. Today's presentation will be given by Yafas Sadiq, who's a technical specialist on the Maya technical team. But before we dive into that, just to make the session a bit more interesting, we're going to run a few polls. So we're going to go into the first poll now. So hopefully you will see a pop-up question bar appear on your screen shortly. And there should be a couple of questions on there. So what is the biggest challenge you face in validating your designs today? And then there's a couple of potential answers. We depend on physical testing to validate our designs. We use simulation too late in our designs. We want to invest in simulation but lack the expertise. We solely depend on tribal data to make engineering decisions. So give you a few seconds to make a choice if you wish to. And once the results come in, with any luck, you should see at some point a window pop up with sort of the results of the different people listening to this webinar. So just give that a few more seconds. As we're waiting, if you've got any, remind you if you've got any questions, ask them. Also, if there's any technical issues, you can post them in the Q&A area, and one of the team will help you with that. Oh, I can see one question. Yeah, so this tribal data, interesting phrase, it's basically historical data or kind of information that is there. Someone, passes that in and no one sort of questions it. It's based on past history. So directly asking you one of the questions. Thank you, James, for asking that. Okay. I'm still waiting for the results here. I'm not sure if there's... Okay. So I've got some, so like I say, hopefully these results should show up. But it looks like option number one, which I guess wouldn't be a surprise to many of us. Yeah, we're depending a lot on physical testing to validate our designs. So thank you for participating, and I'm going to hand over at this point to Yafis, who's going to take us into the meat of the presentation today. So Yafis.
Perfect. Thank you very much, Adam. So essentially, these challenges that were presented in the poll are very common and what we have seen amongst most of our customers, and all of them can be addressed by front-loading simulation. So what exactly is front-loading simulation? Let's look at a typical design cycle. In any given design process, we know that it is much easier to make these design changes early in the design stage, preferably in the conceptual stage, before having developed the prototype, the manufacturing tools, or worse, having produced and delivered products to the customers. Consequently, any defect that's identified later in the design cycle will be more difficult to solve. Now, based on what we have seen and what was reiterated by the poll, many engineering processes depend on prototypes to evaluate their design. But we know that prototypes aren't always available early, and any defect detected by this stage generates significant extra costs and delays. Moreover, given the current situation, since physical testing is limited, we have seen many engineering companies paralyzed due to their dependency on prototypes. The solution to this problem is self-evident. Imagine we were able to, right at the get-go, make design decisions not only from a visual and functional perspective, but based on engineering goals. What if a designer can early in the conceptual phase make informed design decisions based on the performance? This is what front-loading simulation is all about. It is a concept to make simulation available early in the design cycle. One way to do this is essentially providing designers with the simulation tools to ensure they can meet the engineering objectives. Let's see how this has worked out for some of our customers. Renault, by providing designer simulation tools, were able to reduce costs significantly. Their lighting division were able to reduce headlamp costs by 50% within 2 years. Chazzo developed protective housing for various applications. By implementing front-loading simulation, they were able to communicate their design to their customers in less than 1 day, a savings of 3 weeks over the previous method, which was heavily dependent on prototype testing. Mitsubishi Materials Corporation were able to drive innovation through front-loading. Without analyst expertise, their designers were able to increase the flow rate for the cooling systems for advanced cutting tools by 11%. A known customer through front loading were able to automate repeatable simulation processes. They were able to reduce errors and develop an engineering process that was 100 times faster. Clearly, there is value in front-loading simulation. It is important to note that front-loading simulation is multi-domain and can be simply accomplished by redefining our design processes. So I believe the most effective way that I could show the value of front-loading simulation today is through a real engineering problem. Let's take an example of an IGPD module for a vehicle underhood application. I could have selected any engineering problem, but the reason I selected an IGBT module is because designing one is complex and a cross-domain affair between thermal, flow, electromagnetic, and electronics. Moreover, I've helped engineer a few of these at Maya for various clients. Essentially, it's a device that is used in a wide range of industries, in electric vehicle powertrains, wind turbines, refrigerators, to name a few applications. It is used when large amounts of current needs to be switched on and off rapidly. They can generate kilowatts of heat under sustained load. So liquid cooling is the only way to keep them operational and reliable. What we have seen as the major cause of failure in IGPT modules is that, like most electronic devices, is essentially excessive heat. Let's look at the factors taken into consideration when engineering an IGPT. When designing IGPTs, you want to increase the maximum power level and current load capacity while maintaining high quality, reliability, and most importantly, maintain the thermal consideration. Modifying the PCB board on an IGBT to meet thermal constraints is not feasible. Redesigning the cooling system would be the simpler option. So in cooling systems, increasing the flow rate will increase the heat transfer coefficient between the fluid and solid, leading to lower chip temperatures. However, increased flow rates increases the energy consumption of the pumps. Hence, for a given flow rate, designers are challenged to modify the heatsink and pin configurations to ensure it not only maintains the chip temperatures, but also the pressure drop. So a typical workflow we have seen with IGBT manufacturers is that once their product specifications are delivered, designers base their concepts on past designs and tribal data. Thereafter, the validation of the design to meet the engineering requirements is heavily relied on physical testing. Simulation is sometimes used, but this is usually done late in the design cycle and nothing more than a rubber stamp. The major problem that we see with this workflow is that the design defects are detected late in the design cycle only when conducting physical tests. Engineers will now have to return to the iterative cycle with designers making design decisions mostly based on past knowledge and analyst engineering intuition. Any design change to the IGBT cooling system will not only need to meet the thermal requirements, but also the other engineering requirements, such as vibrations, acoustics, to name a few. This means more prototypes leading to increased costs. When the project is few weeks, sometimes days from delivery, what we have seen time and time again is that most engineering firms come to consulting firms like us to resolve these issues. I'm sure many of you listening can relate to this scenario. The engineering team are faced with a difficult task. How do they ensure the designs do not fail based on just tribal information? The design team faces an impossible task. How do they create a new design that won't fail without information on how they will perform? We can easily address both these challenges by using simulation. By equipping engineers with simulation, they will no longer have to rely on tribal data, and providing simulation to designers will ensure they make design decisions based on engineering requirements early in the conceptual phase, or otherwise called front-loading simulation. However, equipping designers with complex simulation tools comes with its challenge. Let's see what they are. So the first challenge is learning a new environment. This increases the simulation from a pure software operation. Second, designers should have the knowledge on setting up the physics problems, maybe CFD, thermal, or structural simulation. These are complex problems and usually need advanced degrees. Another challenge is how can a designer interpret the results to make the changes to improve its performance? This would need collaboration with analysts. So engineering problems are complex and multi-domain. Requirements for components are constantly changing when different systems are integrated into the prototype. This requires the need for full system multi-domain analysis. Designers would have to collaborate with various analyst teams to perform these multi-physics simulations. However, information exchange between designer and analysts has always been an issue. The challenge here is how do we ensure design and simulation data can be easily shared between the two groups in a collaborative environment. Finally, a big concern is how do we redefine our current engineering processes to adopt front-loading simulation. By the end of today's presentation, I hope to address each of these challenges. So the first challenge in front-loading simulation for designers is learning a new environment. We can tackle this by placing simulation in the same environment that the designers are already familiar with, inside the CAD tool itself. Let's see how it looks like in the context of designing an IGBT. This is our IGBT shown in the NX CAD interface. The IGBT has been retrofitted with a cooling system from a previous design. The designer would now send it over to the analyst to validate the thermal constraints and pressure drop. It would be time-saving if the designers could do it themselves. They would need to run a CFD simulation. Before we start, let's first explore the assembly to see the parts which will make up the IGBT cooler. You can see the silicon, the solder, the copper chip carrier, and the thermal base plate, and the aluminum casing. It's going to be important to model all these materials in the thermal path from the semiconductor to the fluid. Let's look at the base plate in more detail. If we open the part, we can see it's been designed very simply in NX. Looking at the NX expressions, we can see that there are three parameters controlling the heatsink: pin width, draft, and pattern spacing. It's been designed this way to modify the heatsink configuration easily. The roadblock to setting up a CFD solution would be using a designer geometry. It's been made with manufacturing tolerances in mind. What this means is that there are some geometrical overlaps between the parts as shown here around the O-ring and the silicon compound. We will need to address this issue. So coming back to our first challenge, simulation tool has to be embedded in the CAD tool. Launching the application, you can see the addition of the flow analysis ribbon toolbar, which will be used to define the CFD problem and post-process the solution entirely within the CAD tool. Let's now address the second challenge, setting up the physics model by a non-expert. In this case, a CFD simulation. Let's start with the first task, creating the fluid volume. Easy for a designer. But to save time, the tool has a geometry functionality to create the fluid region automatically. Moreover, it updates itself if there are any design changes. The next step in the CFD analysis would be setting up the computational domain. This is done through a simple, intuitive, wizard-driven process. It has been designed for non-CFD users in mind. Another important issue is applying material properties. This can be stored in the metadata of the CAD, making applying them a click of a button. Next, the boundary conditions. These can be simply applied directly in the CAD tool. Here we apply the inlet and outlet flow conditions for the liquid cooling systems and the heat load generated by the chips. The next step is traditionally one of the trickiest and the most time-consuming aspects of CFD, meshing. The solid and the fluid parts need to be discretized. Most of the time, geometry needs to be simplified and compromises made for simulation time. To alleviate these issues, the tool uses a technology called Smart Cells applied on a Cartesian-based mesh. Smart Cells can have multiple fluid and solid control volumes in a single cell to simplify the mesh generation step. Complex CAD models are meshed with minimal user input using this automatic mesher. Looking at the conductivity to the model, you can see that Smart Cells can have multiple solids within a single cell, up to 36. This makes resolving thin solids such as thermal interface materials very straightforward and easy. When overlapping parts exist, such as between the O-ring and the base plate, there is a material hierarchy that can be edited to get the material dominance. Essentially, the tool removes the barrier of meshing, allowing non-experts to generate a robust mesh. For this IGBT, there are two key engineering data we want to extract: pressure drop in the cooling module and maximum temperature of the chips. We can set user-defined engineering goals to extract these key performance data points which can be utilized to monitor solution convergence. Let's talk about the solver. Like the measure, the solver uses a proprietary code that shows robust convergence. It captures the boundary layer without consideration of cell size. Additionally, the user does not have to worry about complex solver settings like turbulence models. These have always been a difficult consideration when solving CFD problems. Like all front-loading solutions, the tool is primarily implemented to reduce simulation complexity and promote ease of use. The process is seamless, and the user can expect quick, accurate results with minimal manual intervention. Finally, let's have a look at the results. Like pre-processing, the post-processing is performed within the CAD tool, also for an intuitive user experience. Flow and thermal results can be visualized directly on the assembly, and we can create various plot types. More importantly, this allows you to visualize performance in a way that physical tests cannot. You can really interrogate the results and get the root cause of a flow or thermal issue. From the results, we can see that the IGBT temperatures exceed the required operating conditions. We could easily modify the pins from the expressions, increase the surface area with the fluid, and reduce chip temperature. However, this would increase the pressure drop. The designer would have to iterate through the variables, essentially shoot darts in the dark and hope they get the solution that meets all the requirements. We can resolve this issue through optimization. This will help us find not a good enough solution, but the best solution. Let's see how that's possible. Essentially, the tool has an inbuilt multi-parameter optimizer. The optimizer can leverage the expressions as input variables. We have set up a range for each variable based on manufacturing constraints. Thereafter, we select the goal we would like to optimize, the IGBT temperature, and the pressure drop. We set the constraints for them. Now, all we need to do is run the scenario. In this case, we ran 40 scenarios. The optimizer has its own post-processor. Here we can see all the cases that were run and the respective results. From the Pareto front plot between pressure drop and temperature, what we can see is scenario 37 as the optimal, is 3 degrees lower than the baseline case and within the pressure drop constraint. We can load it as a separate project to visualize the configuration. We can see the denser pin arrangements with steeper draft angle for freer flow. Through this front-loading solution, we can easily be able to identify the best operating point without leaving the CAD tool. Going back to the challenges. To address the challenge of learning a new environment, we introduced CAD embedded solutions. To enable designers setting up complex physics, we introduced workflows that can be used by non-experts. To interpret the results, we have embedded design exploration to explore the design space and get the most optimum design. The issue of changing engineering requirements stems in the fact that simulations are run in a single domain. I showcased how a designer could validate the flow and thermal requirements of the IGBT, but what about structural, acoustics, and vibrations? Before I show you how we can resolve cross-domain front-loading simulation, let's run a poll to see how many here run cross-domain or multi-physics simulation.
Thank you, Yafis, for that the demonstration there. And we'll go into a poll now. So hopefully on your screens, as per last time, you'll get a question. Do you run multi-physics or cross-domain analyses? And you've got a couple of options there. So yes, our solutions are strongly coupled. So that's where you might have tools which are interacting together across a fluids domain, structures domain as they run. Yes, they're weakly coupled, so kind of loose co-simulation maybe, or passing data from one to the other. No, we do not have any coupling in our simulation tools. So basically you're kind of working independently and then maybe bringing the results back together, or you don't use simulation tools. As you're having a chance to answer that question, thank you for the people who are posting questions. We will come to them at the end. There's some good ones there, so keep posting them as we go along. Like I say, we will address them at the end of the session. So I'll give you a few more minutes, or sorry, a few more seconds to fill out the do the poll, and then hopefully we'll get some feedback. Okay, I'm not sure how long the poll results are going to come back, but whilst we're doing that, one quick question for you, Yafis, which came up in your last set, was in the demonstration, was Flow EFD in NX or some other solver? So this is just a specific software question someone's asking.
Yes, so the demonstration that was showed was Flow EFD within NX, but Flow EFD can also be found in other CAD tools like Solid Edge as well.
Excellent. Thank you, Yafis. So, and yeah, we've got some results come back in here. So, quite interesting. So, option, again, hopefully you can see on your screen, but option number 3, which was no, but we do not have any coupling between our simulation tools. It seems to have come back with the highest percentage. So it seems that many of the folks on the call are not kind of currently running multi-physics simulations. So I think in the next section, Yafis, you're going to take us through how you can achieve that and how that might work within the context of this IGBT example. Yafis? Sorry, folks, I believe there's a technical hitch with Yafis's sound. We'll get that sorted a second. Apologies, we're still trying to sort out the sound issue with Yafis. Please bear with us. Okay, so we've made contact with Yafis and he's reconnecting, so we can get him back. whilst we're waiting for Yafis to reconnect, there were a couple other questions come in, so and I can take some of this.
Apologies for that.
Excellent,
yeah,
Yafis.
Back again.
Okay, all right. So I'm gonna hand back to you, and hopefully that won't be any more issues. Thank you, Yafis.
Perfect. No worries. All right. Apologies for that. So essentially, what we had shown earlier is that we had validated the structural integrity of the NewPin component in the CAD environment. And now we can further have some sort of confidence in moving forward with this design. But what I was saying earlier on, another prevalent issue when engineering these IGPDs is that the engineering requirements are constantly changing. Even though the component met the initial requirements, when the full system prototype was being tested, in this case, the IGPD module in the underhood application, they essentially fail. And this pushes engineers to troubleshoot the problem and more often leads to delays and adding costs. We analyze the IGBT as an individual component at a given mass flow rate with a steady thermal load. So these conditions are based on designs in another system. Hello? Can you guys hear me?
Yeah, you're still there, Yafis. Folks, that sounds like we've lost Yafis again. So just whilst he reconnects, figures out a way that the line works. So we had a couple of questions in. I'm just taking a look here. So yeah, I apologize for all the questions here about, so on the presenter side. So does the optimizer, so this is going back to before the poll, you use algorithms from HEEDS? Yes, the answer to that is yes. And I can answer that one. I'm just looking down the list here.
All right, perfect. Adam, I'm back again. Apologies for that.
All right, so, I was just answering a few questions in your absence, Yafis, so sorry about that.
Thank you very much for that. So essentially what I was trying to say is that these problems are always complex and multi-domain, containing electrical systems, control systems, hydraulics, to name a few. The challenge we face is how do we virtually verify a complete system and not just components? How can we front-load accurate engineering decisions much earlier in the design phase? So this can be accomplished by multi-physics simulation. Within our simulations portfolio, we have an integrated scalable platform, system simulation platform, which allows you to do multi-physics simulation, combining electrical, thermal, hydraulics, mechanical, and controls to virtually assess and optimize an entire Megatronic system's performance. The tool can also connect to more detailed analysis solutions like 3D CFD for detailed CFD modeling, or FEA for structural analysis. What this means is that we can apply realistic drive cycles to the IGBT modules with realistic power demand and coolant condition profiles. We can validate the design of the IGBT module while integrating it in a full system simulation without the need for an expensive prototype. This boosts the overall engineering productivity, not only from the early development stage, but until the final performance validation and controls calibration. Now, back to engineering of the IGBT. From our experience, what we reiterated by the poll is we see that most engineering firms do not do multi-physics simulations. However, like all engineering problems, designing an IGBT is multi-physics and a cross-domain problem, including condensation, acoustics, and EMAC considerations at the least. Surprisingly, we have seen companies with great expertise in each physics domain, but still have difficulty in doing multi-physics simulation. Now, this is due to the inability to validate all the physics all at once. Simulation groups are divided based on physics and have difficulty sharing data. There is a lack of collaboration amongst the analysts. Now, this can be resolved by having a well-connected digital twin of all our engineering tools and processes. This is possible through the SimCenter portfolio. SimCenter delivers best-in-class CAE simulation, system simulation, and testing solution that is a combination of $11 billion invested over 11 years. It consists of hundreds of tools in different domains that are well connected, enabling multi-domain, multi-physics simulations such as CFD, dynamics, and motion, and so much more, with design exploration and analytics analysis kept in mind. Now, all these technologies are managed in a PLM context to support collaboration for engineering and development of complex systems. As Adam had mentioned before, we have a dedicated team at Maya for deploying PLM solutions who successfully implemented in large as well as small to medium companies. All the tools we use today in engineering the IGBT are part of the SimCenter portfolio. Now, before I continue to circle back and address the challenges of front-loading, let's run a poll and see what it's like to know more about your engineering processes.
Thank you, Yafis. So we're going, hopefully, again, you should see another poll question. So this one is your engineering simulation process workflow well defined? Yes, we've implemented the concept of front loading. Yes, but it could be improved with front loading. No, our simulation process workflow is constantly changing. And lastly, we do not use simulation. So hopefully that poll has gone out. And whilst we're waiting for the response to come back, one question that caught my eye here, which might be helpful for everyone. Just Yafis, there was a question from one of the attendees, a bit more information about the purpose of an IGBT. A bit more of an engineering interest question, one that, but I thought might be a nice one to cover at this point.
Well, an IGBT is essentially an engineering device that is used for switching current from high load to low load. It's usually used in wind turbines, EV electric powertrains, essentially from AC/DC converters. That's where its main use is. And so because there's a high switching of current, there's excessive heat associated with IGBTs, and that's why engineering one is quite difficult.
Thank you, Yafis, and hopefully that's answered that question with a little more detail. Okay, I'm just waiting for the poll results to come in. Okay, I think you will see what's come up on your screens. So looking at what we've got here, option number 3, which was no, our simulation process workflow is constantly changing, and number 4 are kind of the highest options, but it's fairly evenly spread. So I guess we've got people at different stages in their journey with simulation listening into this. So Yafis, I'll hand back to you.
Perfect. Thanks, Adam. Well, clearly in some sense, I've sold the value of implementing front-loading simulation, but essentially we need to address the issue of redefining clear engineering workflows, and that was option 3 that was required. So let's address this with the example of the IGBT. So earlier I showed you the typical workflow of an IGBT manufacturer and how they were dependent on prototype testing to validate their design. Let's look at the redefined workflow by establishing the concept of front-loading simulation. We're able to now detect defects earlier on, not only in a single component performance, but in the context of full system. Earlier detection before the prototype phase means reduced cost, less dependency on physical prototypes, also faster time to market. Redefining engineering processes with front-loading is a no-brainer. Let's look back into how we resolve the challenges of implementing front-loading simulation. So, addressing the challenges of changing engineering requirements, we introduced SimCenter's integrated simulation platform. It ensures we do full system multi-domain design analysis early on, reducing the errors during prototype phase, and hence less likelihood of changing engineering requirements. Front-loading simulation clearly needs a tighter collaboration between designers and analysts. There needs to be a constant feedback loop of the simulation data with the analysts to get their insights. Now, this can be resolved through managing all the data in a PLM context using a solution called Teamcenter. Now, taking advantage of these front-loading solutions requires redefining engineering processes. There is no one-shoe-fits-all methodology. Each engineering process has different requirements. right? Different roadblocks and different design business challenges. Reworking engineering processes are always complex and is always a challenge. So you need someone with industry experience in doing so. To implement front loading, you need a partner who understands the environment designers and analysts work in, the simulation tools, understands engineering processes, and the tools to streamline data across them. You would also need expertise in implementing these processes, provide training, and provide customized solutions wherever required. And this is exactly where we come in. Maya FCT has a multidisciplinary team who have vast experience in resolving these challenges in all industries. We provide an engineering alignment to help establish an engineering process strategy to maximize business benefits and reduce implementation risk, providing that catalyst you need for business change. Through a simulation assessment, Maya very recently proposed recommendations to a customer to reduce their overall design process from 18 months to under 12 months while positioning them for growth in their focused market. So what does this simulation assessment entail? The first step would involve auditing your current engineering processes, all the way from determining the requirements to the final product, understanding the most important challenges within your business. Our team would then provide a diagnosis by examining the current processes, provide insight on its capabilities, from our industry experience, identify potential points of failure, and determine optimal points for improvement. Within the collaboration of the stakeholder, we would then lay out an implementation plan, imparting our knowledge of industry best practices, providing any necessary training and custom development, while ensuring there is a smooth transition with little to no impact on current business deliverables. And finally, we'll work together to ensure adoption of these new engineering processes and measure its success by keeping track of KPIs, all in the context of PLM. Now, the aim here is to be able to create a digital twin of your engineering process. All of this can be accomplished from your home office through web meetings. Maya has been very successful in helping our partners navigate through the new norm, taking advantage of digital technology to adapt and increase the operational efficiency while at it. Before I end today's presentation, I'd like to leave you with essentially 3 key takeaways. First, is front-loading simulation is not only practical, it is now essential. Second, the world is multi-physics, so should be our simulation. And finally, adopting front-loading simulation is not a one-size-fits-all solution. Maya FCT is there to help. Thank you all for listening. We'll be using the remainder of the time to answer your questions. I'll be passing on to Adam to cover the Q&A section.
Thank you very much, Yafis. Thank you for those who participated in the polls. And we've also got some nice questions that have come in from various attendees. So trying to order these in some kind of logic, but I think a nice one to start with is going back to your first sort of slide, Yafis, and a question talking about the ease of change curve and querying, saying surely it gets harder over time as design freedom is constrained. So I think it's back to that initial slide where you were talking about how change is affected over the process of designing a product.
So essentially, what we're trying to impart from that graph is that before, it's much easier to make a change in the conceptual stage than when the actual product has been designed and the prototypes has been delivered. So the ease of change is much easier in the conceptual phase than later in the design cycle. And so by providing simulation, not at the end of the prototyping stage, but right at the get-go at the design stage, is essentially enables us to make those changes without minimal waste of time as well as costs associated with prototyping.
Okay, thank you, Yafis. We will also respond to the questions, the folks that have asked with written responses as well, and share them where applicable. But then I've got a group of questions here, Yafis, which have come in around Firstly, I think looking at the accuracy of the prediction tool. So, reading you one example here from an attendee. In the first example, how do you know that the predictions are accurate? Isn't there a probability that you're optimizing an incorrect solution? So, if you've got any feedback on that one?
So yeah, that's a very good question. Now, I think one thing that's key to understand when it comes to simulation, that there is always some sort of validation with experimental data with the first set of data, just to give you the confidence. But I think that given the current simulation tools, we've reached to a point where we get a high level of accuracy right at the get-go. And the idea of using the simulation, right at the front, maybe you might be 1 to 2% off, but even when you perform a better result or better an optimization study, you're looking at something that's compared to the baseline. So you'll still get an improved design. It might be 2 to 3% off from real world factors, but there is, I would say, a higher level of confidence in our simulation tools that we're using today than we would do 10 years ago. So in some sense, our tools have become more accurate. And in one way, you do have to validate at the end of of your prototyping stage with some sort of experimental data to give you that confidence in your results.
Thank you, Yafis. And there was a related question to that around anomalies in the design and simulation results, and I think the answer would be similar. And then a kind of nice question here as well. So along the same sort of lines, so why is it a good idea to simplify the implementation of CFD so it can be used by non-experts, given that they may not have the expertise to properly interrogate the results?
Excellent question. So I think one thing that's important, if you look at any given organization, the number of designers in terms of number of people is much larger than analysts. And what we've seen a lot of times is that designs reach a bottleneck with the analysts because there aren't as many analysts to validate all the designs that the designers are sending in. Now, what the designers can do, and especially with the tool that we showed today, is essentially designed for non-expert CFD users. And it does provide you pretty accurate results. I've tested it in a lot of benchmarks with the tools and comparing it with the high-end CFD tools, and it is a well-validated tool. I just believe that sometimes, in my personal opinion, a lot of CFD engineers are afraid to use a tool like that just because it's much easier to use. But in all retrospect, and if you look at the, just the validation of the tool, it's a quite strong tool. Now, why should we give it to designers in the first place? Is to reduce the bottlenecks, that they can right at the get-go be able to see whether their design meets, in this case, the pressure drop. One thing that's pretty key, or making sure that it maintains the thermal gradient. If a designer, with a few clicks of a button, be able to validate that, they can offload the tasks on the analyst, and the analyst can now focus on much more complex multi-physics simulations than a simple, let's say, a CFD or thermal analysis.
Thank you, Yafis, because there's also a related question. So how is this applicable in bigger companies where skills are split between multiple engineers? And I think there's a similar answer, isn't there, about relieving the bottleneck and achieving a kind of efficient front loading of the simulation work.
That's exactly it. And one thing that's important to note is that we're not replacing the analyst here. We're just reducing the bottleneck. We still need analysts to run in the high-end CFD code, and with all the multi-physics capabilities available now, it's important to run, simulations as is, but we would see them in real world, essentially.
Yeah, and I would add to that, we're also looking to kind of reduce the burden on tests, because you remember the first poll result, a lot of design is this, build it, test it cycle. So this helps break that down, because obviously the test is expensive, and if you're going into test, you really want to hope that you get the results you predicted, not results you did not predict. So all of these things help you get to that point, I would add. So okay,
exactly.
Let's check in here. So all right, so yeah, I've just had this is an interesting, maybe more discussional one, but it's true to say different clients have their own processes or lack of them. other ways we can help with that, and how flexible would be the software tools, for example, to fit around different customers' needs, Yafis?
So all the tools that I mentioned today are within the SimCenter portfolio, are essentially open and can be customized. And Maya, as a company, has enabled a lot of companies to basically streamline all these processes. And because they're open and customizable environments, whatever process that you're looking to implement is pretty much possible within the SimCenter portfolio. So it's quite flexible. I'd say we've had customers create custom toolbars, custom windows for their given processes. So I'd say the possibilities are infinite in some ways, but we can definitely have that conversation with you offline and look into what exactly you're trying to implement and see how that can be done.
Thank you, Yafis. And a couple more just to kind of finish up here. So a nice question, will the presentation be available? So I can answer that. Yes, it will be. It will be available as a recording, and you'll be able to get it from the IMechE site or the Maya website after this event. And obviously re-listen and take your time to go over it again. Where can I find out additional information about front-loading simulation? Again, I would suggest going to the Maya website or getting in touch with us, and we could certainly help with more information and ideas around that. So with that, I think we can draw the session to a close. I'd like to say thank you, Yafis, for presenting, and thank you everyone for attending and joining us today. If you have any more questions after the event or want to learn more about what you saw, don't hesitate to contact us. There will be a survey that comes out after this with a couple of quick questions in, and we'd love if you could feedback on what you thought of the presentation. That will help us improve in the future. And also, if you want to get in touch with us, there's plenty of routes which you can do that via. So thank you very much, and goodbye.